Beneath the ice of one of Jupiter's moons lies an ocean holding more water than every sea on Earth combined, and no sunlight has ever touched it. Subscribe if you want more of the cosmos. This is White Space. Settle in a grand tour of the solar system's moons somewhere beneath an unbroken sheet of ice, the size of a continent and kilometers thick. There may be an ocean that has never seen the sun. No light has ever passed through those frozen walls. No wave has ever formed under the heat of a distant star. And yet the water is there, liquid, warm in places, and possibly not empty. This is Europa, the sixth moon of Jupiter. A world smaller than our own moon, yet one that has occupied the imagination of planetary scientists for decades, with a persistence that few other objects in the solar system can match. Europa was first observed in January 1610, when Galileo Galilei turned his handcrafted telescope toward Jupiter and noticed 4 points of light drifting slowly around the giant planet. He could not have guessed what one of those points contained. Over the next 4 centuries, astronomers tracked Europa's orbit, measured its reflectivity, catalogued its spectrum. But it was not until the Voyager missions in the late 1970s, and then more decisively the Galileo spacecraft in the 1990s and early 2000s that the picture of this small moon began to transform into something genuinely astonishing. The Galileo probe detected something unexpected while making repeated flybys of Europa, a signature in the magnetic field consistent with the presence of a conducting liquid beneath the surface. Not just any liquid, salt water, a briny, electrically active ocean hidden under ice, responsive to Jupiter's enormous magnetic environment, in a way that rock or dry ice simply could not be. The finding was not a certainty, but it was strong enough that the scientific consensus has since firmly accepted it. Europa holds a global subsurface ocean. It has more liquid water than all of Earth's oceans combined. The source of heat that keeps this water from freezing is not the sun. Europa orbits Jupiter at an average distance of about 671,000 kilometers, and at that remove solar energy is feeble. Instead, the heat comes from tidal flexing. Jupiter's gravity is so immense, and the gravitational pulls of the neighboring moons Io and Ganymede so carefully timed by their orbital resonance, that Europa's interior is continuously squeezed and released as it moves along its slightly elliptical orbit. This mechanical kneading generates heat, the same physical principle that warms your hands when you press them together and rub. On Europa, this process operates on a planetary scale, keeping the rocky seafloor warm and the water above it liquid. That resonance, called the Laplace resonance, locks Io, Europa and Ganymede in a precise gravitational relationship in which for every orbit Ganymede completes, Europa completes exactly 2 and Io exactly 4. The 3 moons never align simultaneously, and the configuration is self-reinforcing. Any slight perturbation is corrected by mutual gravitational tugs that pull the system back into resonance. This arrangement has been maintained for billions of years, and it will persist for billions more. It is the engine that powers not only Europa's ocean but also Io's extraordinary volcanism and Ganymede's interior heat. How deep does the ice go? Estimates based on the size and structure of impact craters on the surface suggest the frozen shell is somewhere between 10 and 30 kilometers thick. The debate between a thin shell model and a thick shell model has important implications for whether the surface can exchange material with the ocean below, and at what rate. A thin shell, closer to 10 kilometers, would allow warm, buoyant ice to rise to the surface relatively quickly, cycling ocean chemistry upward and delivering oxidants from the surface downward. A thick shell closer to 30 kilometers would make that exchange slower and less frequent. The distinction matters enormously for any potential life in the ocean, because life requires not just water but a sustained supply of chemical energy. and much of that energy on Europa's surface is produced by a process that has nothing to do with the interior. Jupiter's radiation belts bombard Europa's surface continuously with high-energy charged particles. This bombardment splits water molecules in the surface ice into hydrogen and oxygen, and further drives reactions that produce hydrogen peroxide, molecular oxygen, sulfuric acid, and other chemically reactive compounds, oxidants, collectively. On Earth, life exploits oxidants as an energy source, combining them with reduced compounds in reactions that release energy and drive metabolism. If the oxidants produced on Europa's surface can reach the ocean below, either by slow diffusion through the ice shell or by more dramatic mixing events, when the ice deforms and fractures, they could provide a significant energy source for any organisms living in the dark water beneath. The question of whether the ice is thin enough to allow this transport and whether the resulting chemical gradient is steep enough to be biologically useful sits at the center of current Europa research. Below that, the ocean extends downward for perhaps another 100 kilometers. Somewhere at the bottom, where the liquid water meets the silicate rock of Europa's interior, conditions may closely resemble those found along the mid-ocean ridges of Earth, hydrothermal systems where hot water seeps through fractures in the rock, carrying dissolved minerals and chemical energy into the water above. This possibility matters enormously because on Earth those hydrothermal vents support entire ecosystems. Tube worms stretching 2 meters in length. Blind shrimp that navigate by sensing infrared radiation from the vent fluid, mussels and crabs, and the dense mats of sulfur oxidizing bacteria that underpin everything else. All of these organisms survive in complete darkness, deriving their energy not from photosynthesis but from the chemical reactions between the vent fluid and the surrounding seawater. The discovery of these communities at the Galapagos Rift in 1977, almost exactly when Voyager was photographing Europa, permanently expanded the biological imagination. Life, it turned out, did not need the sun. It needed liquid water, a chemical energy gradient, and time. Europa appears to offer at least 2 of those 3. The chemical gradient at Europa's hydrothermal vents, if they exist, would be driven by the reaction between the warm, mineral-laden fluid rising from the rocky seafloor and the cold, oxidant-bearing water above it. On Earth, this reaction between hydrogen sulfide rising from the rock and oxygen dissolved in the ocean water is what tube worms' symbiotic bacteria actually harvest. On Europa, the chemistry might be different. Hydrogen produced by the reaction of water with the rock itself, combined with oxidants delivered from the surface through the ice shell, could drive metabolism in a completely different set of organisms. The specific compounds would depend on the mineral composition of Europa's seafloor and the temperature and pressure of the vent system, neither of which is currently known. But the thermodynamic argument that the energy available from this kind of chemical gradient is more than sufficient to support biology is well established. There is also a second energy source that has received growing attention: the oxidants produced at Europa's surface by radiation and delivered downward through the ice. This is the process by which Jupiter's charged particle bombardment of the surface ice creates hydrogen peroxide, molecular oxygen, and sulfuric acid. If any of these materials can reach the ocean, they represent a powerful chemical fuel for any organisms living in the dark water below. The delivery mechanism, transport through a cold, viscous ice shell, is slow, but Europa's ice has been cycling and refreshing itself for billions of years, and over that timescale even slow transport adds up. This oxidant delivery pathway makes Europa's potential for sustaining life more robust than it would be if the Moon depended only on hydrothermal vents. It provides a second independent energy source that does not require active geology at the seafloor. In 2013, the Hubble Space Telescope detected what appeared to be water vapor rising from the southern polar region of Europa. a plume reaching perhaps 200 kilometers above the surface before dispersing into space. The detection was made using ultraviolet imaging, the same technique used to study auroral activity on the gas giants. Later observations made with the W.M. Keck Observatory spectrograph over 17 separate nights confirmed the presence of water vapor above the Moon's sunlit hemisphere. The inferred rate of outgassing was extraordinary, enough water to fill an Olympic swimming pool in seconds. Whether these plumes originate directly from the ocean below or from local pockets of warm ice is still debated. But the fact that Europa is exhaling material from its interior into space is significant. A spacecraft flying through such a plume could potentially sample the chemistry of the subsurface ocean without ever landing or drilling, an observation strategy that may already have been inadvertently tested. Analysis of data from one of Galileo's closest Europa flybys in 1997, a pass that brought the spacecraft within 200 kilometers of the surface, suggests that Galileo may have passed directly through a plume without the mission's operators recognizing it at the time. The magnetometer and plasma wave instrument data from that flyby show anomalies consistent with a localized concentration of ionized material, which is exactly what a water plume would produce as solar radiation strips electrons from the escaping molecules. On the surface itself, the evidence of an active interior is written in ice. Europa is one of the smoothest bodies in the solar system. It has almost no mountains, no tall scarps, no heavily cratered highlands. The impact craters that do exist are unusually shallow, their floors nearly level with the surrounding terrain. This is because the icy crust, though rigid at the surface, is warm and yielding at depth. Craters that form are slowly relaxed back toward flatness by the viscous behavior of the ice beneath. The absence of large, ancient craters also suggests that Europa's surface is geologically young, perhaps only 50 to 100 million years old, refreshed periodically as the ice shell overturns and renews itself. One of the better preserved impact structures on the surface is called Tyre, a multi-ring feature about 40 kilometers across, surrounded by concentric rings extending outward to a total diameter of about 140 kilometers. The rings are thought to be frozen waves in the ice, produced by the impact energy spreading radially from the crater center. Their shape and spacing encode information about the mechanical properties of the ice at the time of formation, and models of their geometry are consistent with a liquid ocean relatively close to the surface at the time the crater formed. What dominates the surface instead is a network of reddish-brown lines stretching across the white and gray ice. These are linear fractures and ridges formed as the ice shell is pulled apart and pushed together by the tidal forces of Jupiter and the gravitational influence of the other Galilean moons. Some of these features extend for thousands of kilometers, wrapped around the entire moon. Others are shorter, more irregular, cutting across older structures in a way that records the history of successive episodes of stretching and refreezing. The darkest and most reddish of these features appear to be stained by material that has welled up from below, salts and sulfur compounds carried upward through the cracks before freezing in place. Spectral analysis has identified magnesium sulfate and possibly sodium chloride among these surface deposits, ordinary table salt, the same compound that gives Earth's oceans much of their chemistry. Some of the most complex surface features are found in a region called Connemara Chaos, a roughly 800 square kilometer area where the ice surface has broken into distinct plates separated by smoother, darker material that appears to have been liquid at some point. The plates carry fragments of older lineae that were clearly once continuous lineae that were cut apart, and their fragments carried to new positions as the plates moved before everything refroze. Matching those fragments, as geologists might match displaced rock formations across an earth fault, allows the original geometry to be reconstructed. The reconstruction shows that the plates moved apart, rotated and drifted in a way that is almost exactly analogous to what would happen if large ice floes broke apart and drifted across a surface of liquid water or very soft ice. Connemara chaos is one of the most compelling visual arguments for the existence of Europa's ocean, because the surface geometry cannot be explained without invoking a liquid layer at some depth during its formation. There are also features called chaos terrain, more broadly irregular regions, where the surface appears to have broken apart and refrozen in a jumbled arrangement, with blocks of older ice sitting at odd angles amid smooth younger material. These regions are thought to form where the ice above a localized warm spot melts partially or deforms into a slush, allowing the surface blocks to shift before refreezing. They provide perhaps the clearest surface expression of the dynamic contact between the ice shell and the ocean below. Among the smallest but most numerous surface features are the lenticular small oval-shaped domes and depressions only a few kilometers across, scattered across much of Europa's surface. Their name comes from the Latin word for freckle or lens, and their appearance in images has something of the quality of surface blemishes, slight irregularities that catch the eye only when you know to look for them. The leading hypothesis for their formation involves diapirous blobs of warm, buoyant ice rising from the base of the ice shell toward the surface. As the diapir rises, it deforms the overlying ice, producing a dome at the surface if it reaches close enough. Over time, the material spreads slightly and the dome subsides, leaving the characteristic oval depression. If this model is correct, lenticular record the locations where the ice-ocean interface is most actively exchanging material with the surface, the same locations where plumes might emerge and where any organisms living in the ice might find their way into the upper layers. On a larger scale, features like Terra Macula, a dark oval region about 80 by 70 kilometers, may represent areas where the ice shell has thinned sufficiently that brine from below has erupted onto the surface and refrozen in place. The dark color of Terra and similar features is consistent with the salt-enriched material that has been found in the dark lineae material that was once liquid and has since frozen, carrying its dissolved chemistry with it. The topographic structure of Terra suggests that it has subsided slightly below the surrounding surface level, consistent with the removal of material from below as brine rose and spread outward. Europa's environment, beautiful as it is in every image taken of it, is hostile to the point of lethality. Its orbit passes directly through the most intense part of Jupiter's radiation belts. Charged particles spiral around Jupiter's magnetic field lines and slam into Europa's surface continuously, producing a radiation environment roughly equivalent to 1 million times the annual dose a person would receive on Earth. An unprotected human being on Europa's surface would accumulate a lethal radiation dose in a matter of minutes, the surface itself, chilled to around minus 160 degrees Celsius, would present challenges of an entirely different kind. And the equatorial regions of the Moon are lined with tall spires of ice, structures known on Earth as penitentes, formed when sublimation carves the surface into jagged vertical blades. On Europa, these ice towers are thought to reach heights of 15 meters or more, making any landing on the equatorial surface a dangerous proposition for an automated spacecraft. But the more important question about Europa has never been about landing on its surface. It has been about what might exist beneath it. In 2024, the Europa Clipper spacecraft, the largest planetary science mission NASA has ever launched in terms of spacecraft size, began its journey to Jupiter. It will make dozens of close flybys of Europa over several years, some passing within 25 kilometers of the surface, using radar that can penetrate the ice shell, mass spectrometers that can analyze plume material if any is encountered, magnetometers to characterize the ocean's conductivity and salinity, and cameras that will produce the most detailed maps of Europa's surface ever assembled. It will not land, it will not drill, but it will tell us with unprecedented precision whether Europa is the kind of place where life as we understand it could exist. The Clipper's radar sounder operates at frequencies that can penetrate ice to depths of up to 30 kilometers, effectively mapping the boundary between the ice shell and the ocean below. Where the ice is thin enough, the radar echo from the ocean surface. A sharp boundary between frozen and liquid water may be directly detectable. Where the ice is thicker, the radar will map internal layering and identify regions of warm, soft ice that might indicate places where the shell is more actively cycling. The magnetometer will use the same induction technique as the original Galileo measurements, but with far greater sensitivity, characterizing the ocean's depth, salinity, and thickness with quantitative precision that earlier measurements could not achieve. The mass spectrometer, sensitive enough to detect individual molecules, will analyze any material Europa exhales into space, looking for amino acids, fatty acids, or other organic compounds that would indicate biological activity. The comparison to Enceladus is instructive here. Enceladus, Saturn's small, geologically active moon, has already provided a preview of what an ocean world sample might look like. The Cassini spacecraft flew through Enceladus's plumes multiple times and detected not only water but molecular hydrogen, silica nanoparticles, sodium chloride, and a variety of organic compounds, a chemistry consistent with ongoing hydrothermal reactions between hot rock and liquid water at Enceladus's seafloor. These findings made Enceladus the strongest current candidate for habitable conditions beyond Earth. Europa is larger, older, and has a thicker ice shell, but the same basic chemistry likely applies, and the Europa Clipper's instruments are calibrated with the Enceladus findings in mind. If Clipper's results are sufficiently compelling, a follow-on Europa lander mission has been conceptually designed that would touch the surface, dig into the uppermost ice layers, and analyze the chemistry of material that has migrated upward from depth. The radiation environment would limit the lander's functional lifetime to perhaps 20 or 30 days, but that would be enough to perform a battery of chemical and biological assays on material from an ocean that no light has ever touched. That question whether life exists in Europa's ocean is the reason this moon has become one of the most scrutinized objects in the solar system. The answer could be transformative in a way that very few scientific discoveries in human history have been. If life evolved independently in the ocean of Europa, with no connection to Earth, it would mean that life is not a rare accident of one particular planet, but a predictable outcome wherever the conditions are met. And the number of places in the solar system and across the galaxy where those conditions might be met would have to be dramatically revised upward. For now, Europa keeps its secrets beneath its ice. Not everything that passes through our solar system belongs to it. In October 2017, a survey telescope on Haleakala in Hawaii, part of the Pan-STARRS system designed to scan the sky for near-Earth objects, detected something moving through the inner solar system on a trajectory that no solar system object should have. Its path was hyperbolic. It was moving too fast. It had come from interstellar space, from the direction of the constellation Lyra, and it was already leaving. The detection itself was almost accidental. The Pan-STARRS survey was designed and funded to find asteroids that might pose an impact hazard to Earth. Its discovery of an interstellar visitor was a byproduct of that survey's extraordinary sensitivity. The telescope being capable of detecting objects as faint as 22nd magnitude, far beyond anything the eye or a modest instrument could perceive. The object had already passed its closest approach to the Sun on September 9, 2017, more than a month before it was found, and was already receding when it entered the Pan-STARRS catalog. The window for observation was brutally short. By the time the object's interstellar origin was confirmed and the astronomical community had mobilized its resources, Oumuamua was already receding rapidly. Telescopes around the world were redirected to collect as much data as possible before the object faded below the detection threshold of even the largest instruments. The Very Large Telescope in Chile, the Gemini North and South Telescopes, the Keck Observatory in Hawaii, and the Hubble Space Telescope were all enlisted in the observation campaign. Within roughly 3 weeks of discovery, Oumuamua had become too faint to observe in detail with any existing facility. The entire dataset from which all subsequent analysis was derived was collected in this narrow window of a few weeks, by which time the object was already more than 200 million kilometers from Earth and receding at tens of kilometers per second. This urgency shaped every aspect of the science that followed. The light curves, the measurements of how Oumuamua's brightness varied as it tumbled, were the primary source of information about its shape, because no telescope could directly resolve the object. It was far too small and far too distant. The interpretation of those light curves required assumptions about the object's reflectivity, its surface uniformity, and the geometry of its rotation, all of which could only be estimated. The non-gravitational acceleration was derived from precise measurements of the object's position over the observing window, compared against a computed purely gravitational orbit. The difference between the predicted and observed positions was small, but it was consistent and measurable, and multiple independent teams agreed on its magnitude and direction. Everything that has been written about Oumuamua since its discovery has been built on this slender observational foundation, collected in haste by instruments that had not been designed for the task. The object was given a preliminary comet designation, but follow-up observations at the Very Large Telescope in Chile and other observatories around the world found no coma, no cloud of evaporating gas and dust around a bright nucleus. Comets announced themselves with atmosphere. This object was silent. It was reclassified as an asteroid and renamed. The Pan-STARRS team gave it the Hawaiian name Oumuamua, as astronomers scrambled to observe it during the narrow window before it receded beyond the reach of even the largest telescopes. They assembled a profile of an object unlike anything in the solar system catalogue. Its brightness varied dramatically and rapidly by a factor of 10 over a period of roughly 8 hours, suggesting either a highly elongated shape like a cigar or a blade, or a strongly reflective object tumbling through space. Initial models favored the elongated interpretation, with aspect ratios of perhaps 10:1 in length versus width dimensions on the order of 400 meters long by 40 meters wide, roughly the proportions of a skyscraper lying on its side. Later analysis challenged this. An alternative assessment suggested the object might instead be extremely flat, more like a thin disk or a sheet than a cylinder. The shape distinction mattered because it had implications for how the object had formed and what it was made of. A flat object would have a very large surface area relative to its volume, a property that would amplify the effects of radiation pressure from sunlight acting on it. That brought in the second and most confounding property of Oumuamua. As it swung around the sun and began its outbound journey, it was accelerating, not decelerating as a simple gravitational orbit would predict. Something was pushing it. For a comet, this would be easy to explain. Sublimating gas and ice creates a reaction force, a kind of natural rocket thruster that can alter a small body's trajectory. Astronomers call this non-gravitational acceleration. It is well documented in comets. But Oumuamua had shown no signs of outgassing. There was no coma, no tail, no detectable emission of any volatile species despite searches using the most sensitive spectrographs available. The non-gravitational acceleration was real. It was measured independently by multiple teams from optical observations spanning weeks, and it pointed toward radiation pressure, the gentle but real force that photons exert when they strike a surface, as the most physically coherent explanation. This worked if Oumuamua had a very high surface area relative to its mass, consistent with a thin, flat geometry and a low bulk density. This particular combination of properties led a small number of researchers, most prominently the Harvard astronomer Avi Loeb, to propose that Oumuamua could be an artificial object. A light sail, the kind of propulsion system that several private space initiatives have prototyped in Earth orbit. A thin, reflective sheet large enough to be caught by sunlight like a sail catches wind, propelled by photon pressure. Loeb's argument was not that this was the likely explanation, but that it was not obviously excluded by the data and that the scientific community was too quick to dismiss it without examining it rigorously. The counter-argument from the broader community was equally measured. The surface color of Oumuamua, uniformly reddish, consistent with objects in the Kuiper belt that have been processed by cosmic radiation over long time scales, pointed to a natural origin. No radio emissions were detected despite a systematic search by the Breakthrough Listen initiative using the Green Bank telescope, which would have been expected from any object housing active technology. The absence of any artificial signal, combined with the surface reddening that exactly matches well-understood natural processes, pushed the consensus firmly toward a natural explanation. Among the natural explanations, the nitrogen ice hypothesis stands out. A team of researchers proposed that Oumuamua could be composed primarily of solid molecular nitrogen, the same material that forms the Tombaugh-Regio plains on Pluto. Nitrogen ice is bright, consistent with a low reddening surface prior to radiation processing, and it would sublimate very gradually under solar heating, producing exactly the kind of non-gravitational acceleration seen in Oumuamua without releasing enough gas to be detected at the sensitivities available. In this model, Oumuamua would be a fragment of a Pluto-like body in another stellar system, a piece of a distant world, sheared off by a close encounter with its parent star and flung into interstellar space, where it drifted for perhaps tens of millions of years before entering our system by chance. Computer simulations of tidal disruption events show that such encounters can produce elongated, flat fragments and launch them at speeds sufficient to escape the parent stellar system. The same kind of event had been witnessed directly in our solar system in 1994, when comet Shoemaker-Levy 9 passed too close to Jupiter, was pulled apart into 21 separate fragments by tidal forces, and then crashed sequentially into Jupiter's atmosphere over the course of 6 days. The surface color of Oumuamua, uniformly reddish, consistent with objects in the Kuiper belt that have been processed by cosmic radiation over long timescales, point to a natural origin. The reddening is caused by high-energy protons in cosmic rays interacting with organic compounds in the ice or rock surface, producing a class of complex carbon-bearing molecules called tholins. This process takes time, millions to hundreds of millions of years, and it operates on every icy body exposed to the interstellar cosmic ray flux. The degree of reddening seen in Oumuamua is consistent with an exposure time on the order of tens to hundreds of millions of years. Its exit trajectory carried it toward the constellation Pegasus at a velocity of roughly 26 kilometers per second relative to the Sun once solar gravity had finished decelerating its outbound journey. At that speed, it will cross the distance from the Sun to the nearest star in approximately 70,000 years. It will never slow down enough to be captured by another stellar system. It is effectively an eternal wanderer, expelled from one system, a brief visitor to ours, now crossing the void between stars on a journey with no destination. In 2019, the second interstellar object was found, Comet Borisov, discovered by the Crimean amateur astronomer Gennady Borisov using a telescope of his own construction. Unlike Oumuamua, Borisov displayed a clear coma, a visible tail of gas and dust, and behaved like a comet in every expected respect. It was straightforwardly explained. Its detection 2 years after Oumuamua suggested that interstellar objects passed through the inner solar system far more frequently than previously estimated, perhaps several per year at detectable sizes, and far more in the smaller size ranges below detection thresholds. The Vera C. Rubin Observatory in Chile, when it reaches full operational capacity, is expected to detect interstellar objects at a rate of perhaps 1 or 2 per year, allowing statistical studies of their properties and origins that are impossible from a sample of 2. The detection of 2 interstellar objects in 2 years also allows a rough estimate of their spatial density in the galaxy. If the solar system intercepts interstellar objects at the rate that observations imply, the number of such objects per cubic parsec of galactic space must be extraordinarily large. Estimates range from 10 to the 14 to 10 to the 15 objects per cubic parsec, a density that implies every stellar system has ejected a staggering quantity of material over its lifetime. The formation of planetary systems is intrinsically wasteful. The same gravitational interactions that build planets also scatter vast quantities of smaller bodies into interstellar space. Every star system in the galaxy has likely contributed to this interstellar debris field, and every star system has likely been visited by material from thousands of other systems across its history. Some fraction of that visiting material may carry complex chemistry. Some fraction of it, if the conditions during its origin were right, may carry frozen organic compounds. The galaxy is, in this view, not a collection of isolated planetary systems, but a connected network through which material is continuously exchanged, slowly, across enormous distances, over timescales that dwarf human history, but exchanged nonetheless. This has implications that extend well beyond the question of what Oumuamua was made of. If interstellar objects carry organic material from planetary systems, where chemistry has progressed toward complexity, and if they impact planets and moons in other systems, they may seed those bodies with molecular precursors that would otherwise take far longer to develop locally. The degree to which this process, sometimes called lithopanspermia, could transfer not just chemistry, but actual biological material across stellar distances is deeply uncertain. Living organisms would need to survive the ejection process, the long transit through interstellar space and its radiation environment, and the impact at the destination. Each of these stages imposes severe constraints. But the fact that interstellar material crosses between systems at all means the question is not purely theoretical. Oumuamua is now far beyond the reach of any spacecraft. The next interstellar object may already be inbound. Jupiter has 4 large moons. Each of them, had they formed around the Sun instead of a planet, would be a world worth a dedicated chapter in any textbook on planetary science. Io is defined by volcanoes, Europa is defined by its ocean, Callisto is defined by its ancient, undisturbed surface, a record of the solar system's early bombardment preserved with almost no alteration for 4.5 billion years. And Ganymede is defined by simply being the largest, with a diameter of 5,268 kilometers. Ganymede is bigger than the planet Mercury. It is bigger than Pluto by more than 2,000 kilometers. It is the largest moon in the solar system by a significant margin, larger than the second largest moon, Saturn's Titan, by enough that the distinction is unambiguous. Galileo spotted it on the same night in January 1610 that he found the other 3 Galilean moons, though it took several more nights of observation before he recognized that these 4 lights were not stars but moons. The names Io, Europa, Ganymede, and Callisto were proposed by the German astronomer Simon Marius, who had arrived at his own observations of Jupiter's system around the same time as Galileo. The names were drawn from Greek mythology. Ganymede was the cupbearer of the gods, carried to Olympus by Zeus in the form of an eagle. Ganymede orbits Jupiter at a distance of about 1.07 million kilometers, completing one orbit every 7 days and 3 hours. Like the other large Jovian moons, it is tidally locked, always showing the same face toward Jupiter. Its orbital period is in a precise resonance with Io and Europa. For every orbit Ganymede makes, Europa completes 2 and Io completes 4. This resonance has important consequences for the internal heating of all 3 moons. For Ganymede, the heating effect is less dramatic than for Io or Europa. Ganymede is farther from Jupiter and its orbit is more nearly circular, but it contributes to a thermal state that keeps the moon's interior warmer than it would otherwise be. Ganymede's interior is differentiated, separated into distinct layers by density in the same way that Earth and the other rocky planets are. At its center is an iron-rich metallic core, with a radius of roughly 800 kilometers and a temperature exceeding 1,500 degrees Celsius. Around this core is a thick rocky mantle composed of silicate minerals, including forsterite and magnesium-rich olivine, whose composition resembles that of primitive meteorites called enstatite chondrites. Surrounding the rocky mantle is an enormous shell of water ice, perhaps 900 kilometers thick, that makes up a substantial fraction of Ganymede's total volume. The outermost surface is the top of this ice layer, but the ice shell is not uniform. Models of Ganymede's interior, constrained by measurements of its gravity, its magnetic field, and its response to Jupiter's tidal forces, suggest that the ice layer is itself stratified. Different phases of ice formed under different pressures and temperatures may form distinct layers separated from one another by thin zones of salt-enriched liquid water. There may be as many as 4 distinct ocean layers at different depths within the ice shell, each with slightly different salinity and density, each separated from the next by a particular phase of ice that is stable only under specific pressure and temperature conditions. The deepest liquid layer may be in contact with the silicate mantle at the base of the ice shell, while shallower layers are separated from this deepest one by high-pressure ice phases that do not exist anywhere on Earth's surface. This layering makes Ganymede's interior one of the most structurally complex in the outer solar system, a stacked arrangement of ice and brine that goes from the silicate seafloor at depth up through 900 kilometers of increasingly cold and high-pressure material to the frozen surface. The deepest water-bearing zone, the liquid layer closest to the rocky mantle, is where the most interesting chemistry might occur. Salt water in contact with silicate rock and subjected to elevated temperatures can produce a wide range of reactive compounds. Whether this environment is hospitable to life remains speculative, but the combination of liquid water, mineral chemistry, and a heat source is the same combination that defines Earth's most remote and extreme ecosystems. Ganymede's most singular property, the one that distinguishes it from every other moon in the solar system, is its intrinsic magnetic field. It is the only moon known to generate its own magnetosphere, produced by convection in its iron-rich metallic core, in the same way that Earth's field is generated by motions in its liquid iron outer core. Ganymede's field is relatively weak, a surface strength of roughly 750 nanoteslas at the equator, about 2% of Earth's field strength, but it is real and it creates measurable effects. Within Jupiter's enormous magnetosphere, Ganymede's own field carves out a small region of distinct space, its own bubble inside the larger bubble of Jupiter's magnetic environment. When NASA's Juno spacecraft flew past Ganymede in June 2021, the first close flyby of the moon in more than 2 decades, Its instruments recorded the electromagnetic sounds produced by charged particles moving through this nested magnetic structure. The magnetic field also produces auroral activity near Ganymede's polar regions, where charged particles from Jupiter's radiation belts funnel along magnetic field lines and interact with the Moon's thin oxygen atmosphere. Observations by the Hubble Space Telescope have tracked these auroral bands over time and found that they rock back and forth as Jupiter's magnetic field varies, a pendulum-like motion driven by the rhythmic change in the external field. The amplitude of this rocking provided the crucial evidence for a conducting liquid layer beneath the surface. A pure ice shell would allow Ganymede's aurora to rock through a larger angle. The observed smaller amplitude of rocking can only be explained by the presence of a buried conducting layer, salt water, that generates its own magnetic response and partially counteracts Jupiter's varying field. The existence of Ganymede's magnetic field implies that the metallic iron core must still be at least partially liquid and convecting. An entirely solid core cannot sustain dynamo action. The heat driving this convection comes from a combination of primordial heat left over from formation, heat generated by the decay of radioactive isotopes in the silicate material, and the small but non-zero tidal heating contribution from Ganymede's resonance with Io and Europa. Ganymede has been cooling slowly for 4.5 billion years, and its core has been partially freezing over that time. But enough liquid iron remains, and the convection is vigorous enough to maintain the field. The surface of Ganymede presents two visually distinct terrains. The darker regions, Sulci or dark terrain, are heavily cratered and ancient, estimated to be close to 4 billion years old. The two largest dark terrain regions are Galileo Regio and Nicholson Regio, which together cover a significant fraction of the Moon's northern hemisphere. These regions record the bombardment history of the early solar system in their cratered topography. Galileo Regio, named for the astronomer who discovered Ganymede, is the largest dark region on the Moon, a roughly circular area about 3,200 kilometers across. It is covered in craters of all sizes, from the smallest resolvable in existing images up to multi-ring basins tens of kilometers across. The density of craters is high enough that geologists classify it as saturated terrain, a surface that has been struck so many times that new impacts preferentially destroy older craters, rather than adding to an ever-growing accumulation. Within Galileo Regio, the ancient surface has been only minimally modified by anything other than impact bombardment. There are no grooves, no tectonic fractures, no signs of endogenic, internally driven geological activity. Whatever process created the grooved terrain elsewhere on Ganymede either did not reach this region or ended before it could significantly alter the dark terrain surface. The boundary between dark and grooved terrain is often sharp, a well-defined edge where ancient cratered ice meets younger structured grooved terrain. In some places, the grooved terrain cuts across all the dark terrain features, demonstrating that the grooves formed after the dark terrain already existed. In other places, the dark terrain is incised by grooves that run parallel to nearby groove systems in the bright terrain, suggesting that some tectonic deformation reached even into the oldest regions, though not intensely enough to fully resurface them. Mapping these boundaries in detail is one of the primary objectives of the JUICE mission's high-resolution imaging campaign, because the pattern of where grooved terrain formed and where it did not may preserve information about the thermal structure of the ice shell at the time of Ganymede's most active geological period. Some individual groove systems extend for thousands of kilometers, cutting across the dark terrain boundaries and into other groove systems at various angles. recording an extended history of tectonic deformation. These grooved regions are thought to have formed during an earlier period in Ganymede's history, when the Moon's orbit had not yet settled into its current resonance state. Gravitational interactions with Io, Europa, and Jupiter itself periodically stressed the ice shell, stretching it apart and driving enormous fault systems across the surface. Warm ice welled up through these faults and refroze, resurfacing the terrain and erasing the craters that had accumulated before. The transition from the chaotic early period of tectonic activity to the relative quiet of the present likely occurred several billion years ago, when the Laplace resonance locked into its current configuration and the tidal heating of Ganymede stabilized at its present lower level. Among the features catalogued on Ganymede's surface is a structure called the Enki Catena, a chain of 13 overlapping craters arranged in a line nearly 160 kilometers long. This kind of feature is produced when a comet or asteroid is pulled apart by gravitational tidal forces before impact, so that its pieces strike the surface in sequence along the same trajectory. The process is identical to what happened to comet Shoemaker-Levy 9 at Jupiter in 1994, where the same disruption mechanism split the object into fragments that then impacted the planet one after another. The Enki Catena preserves a record of one such event from Ganymede's past, a comet or asteroid captured and shredded by the Moon's gravity, its pieces falling in order along a line. The variation in crater sizes along the chain, with the largest crater near the center of the sequence, reflects the mass distribution within the original impactor, with its densest central region producing the deepest and widest crater. Ganymede's polar regions are coated with deposits of water frost, somewhat brighter than the surrounding terrain. Charged particles flowing along the magnetic field lines concentrate at the poles and bombard the surface there more intensely than elsewhere. This bombardment breaks water molecules out of the surface ice and redistributes them toward the colder polar areas, where they freeze and accumulate as a distinctive frost deposit. The ice at the poles also has an amorphous rather than crystalline structure, a consequence of continuous particle bombardment that disrupts the ordered molecular arrangement before it can fully form. Ganymede's atmosphere is extremely thin, its surface pressure roughly 1 trillion times lower than Earth's at sea level. It consists primarily of molecular and atomic oxygen, produced by the dissociation of water molecules in the ice surface, by ultraviolet solar radiation, and particle bombardment from Jupiter's radiation environment. The light hydrogen released drifts away into space. The heavier oxygen remains, forming a tenuous envelope around the Moon. An atomic hydrogen cloud has been detected extending outward from the surface to distances of several thousand kilometers, a diffuse halo of the lightest element slowly escaping into Jupiter's magnetosphere. The European Space Agency's JUICE mission, Jupiter Icy Moons Explorer, launched in April 2023 and is on a trajectory that will eventually bring it into orbit around Ganymede itself, making it the first spacecraft ever to orbit a moon other than Earth's. It will arrive at Jupiter in 2031 and spend several years studying Ganymede, Callisto, and Europa before entering Ganymede orbit in 2034. Its instruments will map the ocean layers with radar sounding, measure the magnetic field with far greater precision than any previous mission, and characterize the surface in enough detail to determine whether the grooved terrain's formation history matches our current tectonic models. The scientific agenda for Ganymede extends beyond questions of habitability to questions of planetary formation. Ganymede formed in the disk of materials surrounding the young Jupiter, assembled from the same raw ingredients that built the other Galilean moons. The fact that it is differentiated, that it's separated into a metallic core, rocky mantle, and ice shell, tells us that it was once hot enough for these materials to segregate by density. The heat that drove this differentiation came primarily from the impacts of the bodies that accreted to form Ganymede itself, supplemented by the heat of Jupiter's own luminosity during the early phase of its formation. The composition of Ganymede's ice, which includes not only water but trace amounts of ammonia and carbon dioxide, reflects the temperature and composition of the material available at Ganymede's orbital distance when the Moon was forming. Reading this composition in detail, as JUICE will attempt to do, is equivalent to reading a record of conditions in the early Jovian subnebula, a dataset that cannot be recovered any other way. The question of whether Ganymede's layered ocean could support life is more difficult to answer than the equivalent question for Europa. On Europa, the ocean floor is in contact with rock, the same rock-water interface that hosts hydrothermal vents on Earth. On Ganymede, the deepest ocean layer may be bounded below not by rock but by high-pressure ice, a form of ice that is denser than the water above it, stable only under the enormous pressures at those depths. If the deepest liquid layer is isolated from the rocky interior by this high-pressure ice layer, the chemical exchange between rock and water that drives hydrothermal chemistry would be blocked. Life in the deepest Ganymede ocean, if it existed, would need to survive on whatever chemical energy diffuses through the ice, a much weaker gradient than a direct rock-water contact provides. This is one of the reasons that Europa, despite being smaller and less geologically interesting in many other respects, is considered a more compelling astrobiological target. Its ocean directly contacts its rocky seafloor. Ganymede's may not. The resources that Ganymede potentially offers vast quantities of water ice, an accessible silicate interior for mineral extraction, a magnetic field to orient navigation, give it a theoretical appeal as a base for deeper exploration of the Jovian system in any imagined future of extended human spaceflight, but that future is distant. For now, Ganymede remains a destination for robots and the patient science of remote observation. Beyond Jupiter, the solar system changes in character. The asteroid belt thins and the distances between things grow. Saturn, at 9.5 astronomical units from the Sun, is the second of the gas giants and the most visually arresting object in the solar system when seen through even a modest telescope. Saturn's ring system is one of the solar system's most iconic structures, and also one of its most poorly understood. The rings extend from about 7,000 kilometers above Saturn's cloud tops to a distance of more than 400,000 kilometers, a span larger than the distance from Earth to the Moon. Despite their enormous extent, the rings are extraordinarily thin in most places, no more than 10 to 100 meters thick, a ratio of width to thickness that makes them proportionally far flatter than a sheet of paper. They are made almost entirely of water ice particles, ranging in size from dust grains to objects several meters across, with a small admixture of rocky material and organic compounds that give some ring regions a slight brownish color. The rings are not static. The particles that make them up orbit Saturn at different speeds depending on their distance from the planet, as Newton's laws predict, and they interact with one another through frequent low-velocity collisions that continuously redistribute material and maintain the ring's flat geometry. The age of the rings has been the subject of intense debate. Early estimates suggested they might be nearly as old as the solar system itself. More recent analysis of data from the Cassini spacecraft, which orbited Saturn from 2004 to 2017 and ended its mission by deliberately flying into Saturn's atmosphere, suggests the rings are surprisingly young, perhaps only 100 to 400 million years ago. If this is correct, the rings formed well after the solar system's early history, likely from the tidal disruption of a comet, asteroid, or a small icy moon that wandered too close to Saturn. This would mean that when the first dinosaurs appeared on Earth, Saturn had no visible rings at all. The rings are also disappearing. Saturn's gravity and magnetic field are pulling ring material downward into the planet at the rate that the Cassini mission measured at about 10,000 kilograms per second. This process, called ring rain, was discovered when Cassini flew between the rings and Saturn's upper atmosphere during its final series of orbits, called the grand finale. The spacecraft detected streams of charged particles flowing along magnetic field lines from the inner edge of the rings downward into Saturn's ionosphere. Analysis of the collected material confirmed that it included water, carbon dioxide, hydrogen cyanide, and organic compounds, a rich mixture of ring chemistry delivered directly into the planet's atmosphere. At the measured rate, the rings would completely drain into Saturn in roughly 100 million years, reinforcing the conclusion that they are a temporary feature rather than a permanent one. The Cassini grand finale orbits also provided the first direct measurements of Saturn's gravitational field with enough precision to constrain the depth of its atmospheric bands and the rotation rate of its interior, questions that had been debated for decades. It was during these final orbits that Cassini sampled the ring material directly, measured the mass of the ring system accurately for the first time, and confirmed that the ring's total mass is only about 40% of the mass of the Mimas. This low mass, combined with the young age implied by the ring rain rate and the brightness and compositional purity of the ring ice, points consistently toward a formation event that occurred well within the current era of complex life on Earth. The solar system of 100 million years from now will be a different place. Saturn without its rings, orbited by a different configuration of moonlets whose gravitational interactions with the ring material would have changed as the rings dissipated. The current ring system, the structure that has defined Saturn's visual identity for every human being who has ever looked through a telescope, is a transient phenomenon. We happen to live at the right moment in solar system history to see it in its current brilliant state. Delineating the rings are several gaps, the widest of which is the Cassini division, a dark band about 4,800 kilometers wide separating the two brightest rings. It exists because of orbital resonance with Saturn's innermost major moon. Mimas, a particle in the Cassini division, would have an orbital period exactly half that of Mimas. Because of this resonance, Mimas's gravitational pull nudges such particles repeatedly in the same direction at regular intervals, gradually destabilizing their orbits and clearing them from the resonance zone. Mimas itself is the smallest of Saturn's 8 major moons and the innermost. It was discovered in 1789 by William Herschel using a reflecting telescope of his own design. At 396 kilometers in diameter, Mimas barely reaches the threshold of hydrostatic equilibrium, the condition where self-gravity pulls an object into a roughly spherical shape. It is the smallest known body in the solar system to have achieved this spherical form through self-gravitation alone. Its internal structure is dominated by water ice with very little rock mixed in. The moon's low density, only about 1.15 times that of water, is consistent with a composition that is roughly 90% water ice with a small fraction of silicate material. The surface temperature in daytime reaches around minus 100 degrees Celsius and plunges to minus 220 degrees Celsius on the night side, one of the steepest day-night temperature contrasts in the outer solar system. What makes Mimas famous is not its composition but its appearance. Mimas bears an impact crater named Herschel, in honor of its discoverer, that stretches 190 kilometers across its face. The crater is enormous relative to the moon itself. Its diameter is roughly a third of the moon's total diameter. The impact wall rises up to 10 kilometers above the crater floor in places. The central peak at the crater's center rises to about 6 kilometers taller than Kilimanjaro. On the opposite side of the moon from Herschel, a pattern of deep fractures marks the surface, the result of seismic waves that radiated outward from the impact, traveled around and through the moon, and converged on the far side with enough energy to crack the ice. The impactor that created Herschel came close enough to shattering Mimas entirely, that the survival of the Moon is itself geologically noteworthy. The resemblance of Mimas, with its enormous circular crater and domed central peak, to the Death Star space station from the 1977 film Star Wars, has been noted so often that it has become a standard observation in popular accounts of the Moon. The similarity is purely coincidental. The film predates the detailed imaging of Mimas by the Voyager 1 spacecraft in 1980 by 3 years. But the comparison has stuck, and Mimas has achieved a degree of public recognition that many scientifically more important bodies lack. The Cassini mission added an additional surprise to Mimas's profile. Thermal imaging of the Moon's surface revealed a temperature pattern that did not match what simple models of sunlight heating a cratered ice ball would predict. The warmest region on Mimas, the region receiving the most solar heating, was not where the thermal data said it should be. Instead, the temperature map showed a distinctive pattern, a warmer zone shaped somewhat like the video game character Pac-Man, with the Herschel crater sitting in the position of the eye. This became informally known as the Pac-Man thermal anomaly. The explanation involves the unusual properties of Mimas's surface material, which is so loosely packed and thermally insulating in some regions that it heats up rapidly in sunlight, but also cools rapidly, producing a temperature distribution that does not follow the naive expectation from simple geometry. But it has also been proposed that the anomaly could reflect a warmer interior, perhaps again a subsurface ocean. Despite its relatively simple appearance, Mimas has surprised scientists with the behavior of its libration, a slight wobbling in its rotation that is detectable by tracking surface feature positions over time. Mimas liberates more than models of a simple, uniform ice ball predict. One explanation is an unusual non-spherical rocky core. Another, more intriguing explanation is that Mimas harbors a liquid water ocean beneath its icy surface, an ocean that would rock slightly in response to gravitational forces producing the observed oscillation. If the latter is true, Mimas would join Europa, Ganymede, and Enceladus in the growing list of icy bodies in the outer solar system concealing internal oceans. Enceladus deserves at least a passing mention here because it represents perhaps the single most dramatic discovery of the Cassini mission. This small moon, only 504 kilometers in diameter, even smaller than Mimas, sprays enormous jets of water vapor and ice particles from its southern polar region into space, feeding Saturn's outermost E-ring with a continuous supply of fresh material. The jets originate from fractures in the southern polar ice, dubbed tiger stripes, where tidal heating from Saturn maintains liquid water close to the surface. The Cassini spacecraft flew through these plumes multiple times and detected sodium chloride, silica nanoparticles, molecular hydrogen, and organic compounds in the spray, a chemistry strongly suggestive of hydrothermal activity at Enceladus' seafloor. In terms of astrobiological potential, Enceladus is arguably the most compelling target in the solar system. Saturn's other large moon, Titan, offers a different kind of strangeness, with a diameter of 5,150 kilometers. Titan is only slightly smaller than Ganymede and is the second largest moon in the solar system. It has a thick nitrogen atmosphere denser at the surface than Earth's, with a surface pressure about 1.5 times that of Earth at sea level. The Cassini mission spent 13 years studying Titan and discovered a world whose surface is shaped not by water, but by liquid methane. Rivers of methane carve channels across the landscape, lakes and seas of liquid methane and ethane fill depressions near the poles, and methane rain falls seasonally. The Huygens probe, released by Cassini, descended through Titan's atmosphere in January 2005 and transmitted images of a landscape eerily reminiscent of Earth, river valleys, a shoreline, rounded pebbles of water ice, shaped by fluid flow, but composed of chemistry that would be toxic and incomprehensible to any terrestrial organism. Whether life could exist in Titan's methane seas using a solvent other than water and chemistry, fundamentally different from anything known on Earth, is an open question that some theoretical biologists have taken seriously. NASA's Dragonfly mission, a rotorcraft lander scheduled for launch in 2028, will fly through Titan's thick atmosphere to multiple sites, analyzing the chemistry of the surface for signs of prebiotic or biotic processes. The Cassini mission itself, which orbited Saturn from 2004 to September 2017, is one of the most scientifically productive planetary missions in history. Its discovery of Enceladus's active ocean, its detailed characterization of Titan's methane cycle, its measurement of Saturn's rotation rate, its observation of the ring dynamics, its tracking of storm systems that appeared and evolved over years. All of these findings transformed our understanding of the Saturn system far more profoundly than the brief Voyager flybys of 1980 and 1981 had. The mission ended when Cassini ran out of propellant and was deliberately guided into Saturn's atmosphere. Vaporized at supersonic speed, a controlled disposal designed to prevent the spacecraft from contaminating Titan or Enceladus with any terrestrial biological material that might have survived the journey from Earth. Mimas currently has no warm spot, no active geysers, no surface feature that would betray an ocean if one exists. But the liberation data has not gone away, and the question remains open. Between Mars and Jupiter, the solar system contains a vast region populated by hundreds of thousands of rocky and metallic objects, the asteroid belt. The belt stretches across a band of space roughly 300 million kilometers wide, between 2.1 and 3.3 astronomical units from the Sun. Its total mass is modest. All the objects in the main belt combined amount to roughly 4% of the mass of the Moon. More than half of that total mass is concentrated in the four largest bodies, Ceres, Vesta, Pallas, and Hygiea. The distribution of objects within the belt is not uniform. There are several zones of conspicuous emptiness called Kirkwood gaps, regions where the orbital period would be a simple fraction of Jupiter's orbital period. Objects whose orbits place them in these resonances receive periodic gravitational nudges from Jupiter in the same direction at regular intervals, steadily increasing the eccentricity of their orbits until they are eventually perturbed into trajectories that intersect the inner solar system. The Kirkwood gaps are, in effect, Jupiter's signature inscribed across the asteroid belt, a record of the giant planet's gravitational dominance over the entire inner solar system. Beyond the main belt, at Jupiter's own orbital distance, two large populations of asteroids cluster at the L4 and L5 Lagrange points, gravitational sweet spots that lead and trail Jupiter in its orbit by 60 degrees. These are the Trojan asteroids, collectively containing roughly as much total mass as the main belt. They have been in their current positions for billions of years, stabilized by the combined gravitational influence of Jupiter and the Sun. The Dawn spacecraft's ion thruster technology was partly developed in anticipation of eventual missions to these trapped populations. NASA's Lucy mission, launched in 2021, is currently on a trajectory to visit 6 of the Trojan asteroids during the 2020s and 2030s, making it the first mission specifically designed to study this population. The idea that the asteroid belt represents the ruins of a planet that was prevented from forming by Jupiter's gravity has largely been replaced by a more nuanced picture. Jupiter's gravitational influence did disrupt the region during the solar system's early history, but not by preventing a planet from accumulating, rather by scattering material so that collisions between objects in the belt occurred at velocities too high for accretion to proceed. The total mass of the belt today is far less than it was during the early solar system, most of it having been ejected into other orbits by the same gravitational influences that continue to shape the belt today. The first spacecraft to transit the asteroid belt was Pioneer 10, which crossed the region in July 1972 and found the feared density of debris insufficient to threaten the spacecraft. Later missions crossing the belt, Voyager 1, Voyager 2, Ulysses, Galileo similarly traversed it without incident. The objects in the belt are spread across such an enormous volume of space that the average distance between them is measured in hundreds of thousands of kilometers. In 2007, NASA launched the Dawn spacecraft on a mission to orbit two of the largest asteroid belt objects, Vesta and Ceres. Dawn was the first spacecraft to orbit two separate extraterrestrial bodies in succession, using an ion propulsion system that burned xenon propellant at very low thrust, but very high efficiency over long periods. The ion engine worked by stripping electrons from xenon atoms to create positively charged ions, then accelerating them through an electric field. The exhaust velocity was roughly 10 times higher than a conventional chemical rocket, which meant that for a given mass of propellant, the ion engine could change the spacecraft's velocity by 10 times as much. The trade-off was thrust. The engine produced barely enough force to lift a piece of paper against Earth's gravity. Over months and years of continuous operation, this whisper of a push accumulated into the substantial velocity changes needed to navigate between asteroid belt targets. Vesta is the second largest body in the main asteroid belt, with a mean diameter of about 525 kilometers, and a distinctly irregular shape that reflects the catastrophic impacts it has sustained over its history. The most striking feature in Vesta's southern hemisphere is the Rhea Silvia impact basin, a crater approximately 500 kilometers across and 19 kilometers deep, so large that its diameter nearly equals Vesta's own average diameter. At the center of Rhea Silvia is a central peak roughly 22 kilometers tall, making it one of the tallest mountains in the solar system. A second overlapping basin, older and partly buried beneath Rhea Silvia called Venenea, records an even earlier impact. These two impacts reshaped Vesta profoundly. They ejected enormous quantities of material enough to produce a distinct family of smaller asteroids in the main belt, identified by their similar orbits and compositions that are likely fragments of the two collisions. Data from Dawn confirm that Vesta is compositionally differentiated. It has an iron-nickel core, a rocky mantle, and a crust that has been battered and partially stripped by the two major impacts. The northern hemisphere is ancient crater terrain. The southern hemisphere was effectively resurfaced by the Rhea Silvia impact. One of Dawn's more unexpected findings at Vesta was the detection of hydrated minerals, compounds that incorporate water molecules into their crystal structure. Vesta was expected to be dry, having formed in the hotter inner part of the solar system. The hydrated minerals appear to have been delivered by carbon-rich meteorites that struck Vesta and left their chemistry behind. Even an object like Vesta, rocky, ancient, and apparently arid, retains a record of its interactions with water-bearing material from the outer solar system. After leaving Vesta orbit, Dawn spent 2.5 years traveling outward to Ceres, arriving in March 2015 and becoming the first spacecraft to orbit a dwarf planet. Ceres occupies a unique position, large enough to be classified as a dwarf planet under the IAU definition. It is by far the largest body in the main asteroid belt and has a spherical shape maintained by its own gravity. With a diameter of about 945 kilometers, it is large enough to have retained water ice beneath its surface and to show evidence of ongoing geological activity. When Dawn entered orbit and began systematic imaging, it found something striking: a large number of bright spots on the surface, concentrated in certain crater floors but scattered widely. The brightest cluster of spots sits inside the 92-kilometer Occator crater. Dawn's instruments identified these spots as deposits of sodium carbonate, a salt whose presence in such quantity and in such specific locations pointed to a geological process that had delivered brine from the interior to the surface. The proposed mechanism involves hydrothermal activity. Ceres retains enough internal heat from radioactive decay to maintain a liquid brine layer below a thick ice shell. When an impactor punches through the ice, brine rises through the fractures and evaporates, leaving behind salt deposits as the volatile water sublimes away. Dawn also found a solitary mountain on Ceres Ahona Mons, a dome-shaped structure about 4 kilometers tall and about 17 kilometers across at its base. Its steep sides and bright, salt-streaked surface suggest that Ahona Mons is a cryovolcanic dome built up by repeated extrusions of water-rich slurry from the interior. If this interpretation is correct, Ceres is geologically active, still processing its interior material beyond Vesta and Ceres. The asteroid belt contains objects of far more exotic composition. In the outer belt, a population of metallic asteroids, bodies composed primarily of iron and nickel, represents what may be the exposed cores of differentiated planetesimals that were shattered by collisions early in solar system history. The largest of these is 16 Psyche, a roughly potato-shaped metallic body about 280 kilometers across. Psyche may represent the iron core of a protoplanet that had its silicate mantle stripped away by repeated giant impacts, before it could grow into a full-sized planet. NASA's Psyche mission, which launched in October 2023 and will arrive at the asteroid in 2029, aims to characterize the surface composition and interior structure of Psyche in enough detail to determine whether this core world hypothesis is correct. In the past decade, 2 asteroid sample return missions have brought pristine material from specific asteroids back to Earth for laboratory analysis. The Japanese Hayabusa 2 mission collected material from the carbon-rich asteroid Ryugu in 2019 and returned it to Earth in December 2020. Analysis of the Ryugu samples found amino acids, hydrated silicates, and organic compounds, confirming that carbon-rich asteroids contain the chemical precursors of life and that these materials can survive millions of years of exposure to the space environment. NASA's OSIRIS-REx mission collected material from the asteroid Bennu in 2020 and returned it to Earth in September 2023. Bennu samples likewise contained hydrated clay minerals and carbon compounds. These missions have not proven that life exists beyond Earth, but they have demonstrated that the building blocks of life are distributed throughout the solar system and delivered to planets by asteroid impacts, including the impacts that shaped the early Earth. Bennu itself offered additional surprises during the OSIRIS-REx mission. Close-range imaging revealed that the asteroid's surface is covered in boulders far larger and in far greater numbers than pre-mission estimates had predicted. The surface material was also unexpectedly loose and weakly cohesive. When the spacecraft's sampling arm touched the surface to collect material, it sank almost half a meter into the regolith before the gas burst mechanism activated. This suggested that Bennu's surface layer is essentially a rubble pile with very low bulk density, more like a collection of loosely aggregated fragments than a solid rock surface. This finding has implications not just for sample return science, but for planetary defense. Any spacecraft mission attempting to deflect a rubble pile asteroid by direct impact or gravitational tractor would need to account for the energy-absorbing properties of a loosely consolidated surface. The asteroid belt also contains a significant population of binary systems, pairs of asteroids orbiting each other. It is estimated that perhaps 15% of near-Earth asteroids and a comparable fraction of main belt asteroids are binaries. These systems form through several mechanisms, the most common being the Yorp effect. a subtle torsional acceleration caused by the asymmetric emission of thermal radiation from an irregular asteroid surface. As a slowly rotating asteroid is spun up by this effect over millions of years, material at its equator eventually exceeds the escape velocity and is shed into orbit, forming a smaller companion. Binary asteroids are scientifically valuable because the orbital dynamics of the pair allow the masses of both bodies to be determined precisely, information that is otherwise very difficult to obtain for small solar system objects. The near-Earth asteroid population, of which Bennu is a member, deserves specific attention because it represents the subset of the asteroid belt most directly relevant to Earth's future. Near-Earth asteroids are bodies whose orbits bring them within 1.3 astronomical units of the Sun, crossing or approaching Earth's orbit. The current catalog contains more than 32,000 known near-Earth asteroids, of which roughly 2,000 are classified as potentially hazardous, large enough, and with orbital characteristics close enough to Earth's orbit that future impacts cannot be ruled out over millennia-long timescales. In September 2022, NASA demonstrated that the trajectory of a near-Earth asteroid could be deliberately changed. The DART spacecraft, Double Asteroid Redirection Test, deliberately impacted the moonlet Dimorphos, which orbits the larger asteroid Didymos, at a speed of roughly 6.1 kilometers per second. The impact shifted Dimorphos's orbital period around Didymos by 33 minutes. Far more than the minimum measurable threshold that would have counted as a success. Ground-based and space-based telescopes measured the orbital period change directly, and subsequent observations revealed that the impact had also ejected a substantial cloud of material boulders, pebbles, and fine debris that trailed Dimorphos in its orbit for months afterward. The ejected material contributed to the momentum transfer more than the impact alone would have, amplifying the deflection effect. The DART mission proved for the first time that a kinetic impactor is a viable planetary defense technique, that if a dangerous asteroid is detected with sufficient lead time, a spacecraft can meaningfully alter its course. The European Space Agency's follow-on mission, Hera, will arrive at the Didymos system in 2026 to characterize the crater left by DART and measure the internal structure of Dimorphos in detail, information needed to understand exactly how the momentum transfer worked and how to optimize future deflection missions for different types of asteroid. Together, DART and Hera represent the first complete planetary defense test in history: threat identification, deflection, execution, and post-deflection characterization. The probability of any individual asteroid impacting Earth in the next century is extremely small, but the catalog is still incomplete at the smaller end of the size distribution, and the consequences of an undetected impactor arriving without warning would be severe. Dawn's mission ended in November 2018 when the spacecraft exhausted its supply of hydrazine attitude control propellant. It accumulated 69,000 images and 132 gigabytes of data. It transformed two objects that had been points of light in observatory records for 2 centuries into fully realized worlds with complex geological histories. In 11 years of operation, it traveled more than 6.9 billion kilometers. It now orbits Ceres in permanent silence, completing the mission by becoming part of the world it studied. At the edge of the solar system's familiar territory, past the asteroid belt, past Jupiter and Saturn and Uranus, lies Neptune. At 30 times the distance from Earth to the Sun, it is a planet that takes 165 years to complete one orbit. Its discovery in 1846 was one of the most dramatic triumphs of Newtonian mechanics. Astronomers had noticed that Uranus did not follow the orbit predicted by calculations, and a French mathematician named Urbain Le Verrier solved the equations to determine where an undiscovered planet must lie to produce the observed perturbations. When Johann Galle pointed a telescope at the predicted position, Neptune was found within 1 degree of Leverrier's calculation. It was the first planet located by mathematics before it was seen through glass. Only one spacecraft has ever visited it, Voyager 2, which made its closest approach in August 1989, flew past the planet and its system of moons in a few hours and has been receding from the solar system ever since. In that brief encounter, Voyager 2 confirmed that Neptune has the strongest winds of any planet in the solar system, jet streams exceeding 2,000 kilometers per hour, and discovered a large storm system, the Great Dark Spot, analogous in form to Jupiter's Great Red Spot, but since disappeared. It also photographed Neptune's largest moon, Triton, in enough detail to reveal a world unlike anything seen before. Neptune itself is not a destination for habitation. Its atmosphere offers no surface, no stable base, and no accessible chemistry. The gravitational pull at the cloud tops is only slightly stronger than Earth's, about 17% more. But what lies below is hundreds of kilometers of increasingly dense and hot gas, transitioning into a mantle of hot, high-pressure water and ammonia before reaching a rocky core with temperatures around 5,000 degrees Celsius. Its largest moon is a different matter. Triton is a world of extremes, and it draws attention precisely because it does not fit the mold of other large moons in the outer solar system. Triton orbits Neptune in the opposite direction of the planet's rotation, a retrograde orbit that no large moon formed in place around its host planet would have. This means Triton was not born at Neptune. It was captured, gravitationally snared by Neptune after wandering into its vicinity from elsewhere. The most likely origin is the Kuiper belt, the disk of icy bodies that extends beyond Neptune's orbit. Triton may once have been a Kuiper belt object, a cousin of Pluto, before Neptune's gravity seized it and drew it into its current tight, retrograde, nearly circular orbit. The capture process would have been violent, likely requiring a collision or close encounter between the incoming object and an original moon of Neptune, or perhaps between two Kuiper belt objects in Neptune's vicinity, with one being captured and the other ejected. The orbital energy that was not carried off by the ejected body would have been dissipated through tidal interactions with Neptune over millions of years, gradually circularizing Triton's initially highly elliptical capture orbit into the nearly circular orbit it occupies today. Triton's diameter is 2,706 kilometers, making it larger than Pluto. Triton's atmosphere is thin. Surface pressure is roughly 70,000 times lower than Earth's at sea level, composed primarily of nitrogen, with small amounts of methane and carbon monoxide. Like Pluto, Triton has ices of nitrogen, methane, and carbon monoxide on its surface. During the long southern summer, Triton's south pole has been in sunlight for decades, as Neptune makes its slow 165-year orbit. These surface ices sublimate and contribute to the thickening of the atmosphere, with a mean surface temperature of about minus 235 degrees Celsius. Triton is the coldest body in the solar system that has been directly measured. It is colder than Pluto, colder than any point on any other world we have visited. At that temperature, nitrogen is solid. What sublimation occurs is driven by what little solar energy reaches that distance, about 900 times less than Earth receives. Yet even this faint solar energy is enough to power geological activity on Triton. Voyager 2 photographed dark streaks on Triton's surface, elongated marks pointing downwind from small dark spots. These were interpreted as the remnants of geyser-like eruptions. Solar heating of the nitrogen ice beneath Triton's thin, transparent outer crust causes the deeper ice to warm and sublimate, building up gas pressure until it eventually vents through the surface. The erupting gas carries dark organic material upward in a column that rises roughly 8 kilometers before the erupting material is blown downwind by high-altitude nitrogen winds. The resulting dark streak can extend for tens of kilometers across the surface. Voyager 2 imaged 2 active plumes in the South Polar region in real time, their columns visible against the haze of Triton's thin atmosphere. This is not volcanism in any familiar sense. It is a process driven by sunlight acting on a surface that is barely above absolute zero, and it makes Triton one of only a handful of solar system objects on which active geological processes have been directly observed. The comparison between Triton and Pluto is instructive. The two bodies are similar in size, similar in bulk composition, and may have had similar histories before Triton's capture by Neptune altered its fate. Pluto, which has remained in the Kuiper belt and has never been subjected to the tidal stresses of a planetary encounter, shows a surface dominated by a large bright nitrogen ice plain, Tumbo Regio, alongside older, more heavily cratered terrain. Triton lacks a comparable large bright plain. Its southern polar region is dominated by the pink-tinged nitrogen frost deposits of the current summer season rather than a persistent bright basin. The difference may reflect the thermal processing that Triton experienced during its capture and orbital circularization, which would have temporarily heated its interior to a degree that Pluto's did not experience, or it may simply reflect the different observational geometries. Voyager 2 saw Triton's summer hemisphere, while New Horizons mapped Pluto in its northern summer. The comparison between the two would be most meaningful if Triton's winter hemisphere could be imaged with modern instruments, revealing how different or similar the two Kuiper belt cousins really are beneath their seasonal surface chemistry. Triton's surface is a mosaic of terrains. The southern hemisphere shows relatively smooth frozen plains with few craters. The nitrogen, methane, carbon monoxide ice deposits that accumulate during the hemisphere's summer and reflect most of the sunlight that reaches them, keeping the surface as cold as it is despite the seasonal insolation. The northern hemisphere shows older, more cratered terrain and a distinctive region called cantaloupe terrain, a surface covered in rounded irregular depressions closely spaced across an area roughly 500 kilometers across. The depressions average about 30 to 40 kilometers across, and nothing quite like this terrain has been found anywhere else in the solar system. Its origin may involve diapirism, the slow upward movement of warmer, less dense ice through denser overlying material, creating rounded domes and troughs as the material migrates, or it may record the intense geologic processing that followed Triton's capture by Neptune. Triton's retrograde orbit means it is slowly losing altitude. Every orbit, tidal forces transfer angular momentum from Triton's orbit to Neptune's rotation, gradually bringing Triton closer to the planet. In approximately 3.6 billion years, Triton will cross the Roche limit, the distance at which Neptune's tidal forces will exceed the gravitational cohesion of Triton's own body. At that point, Triton will be pulled apart. Its material will spread into a ring system around Neptune that will dramatically exceed Saturn's rings in its initial density before gradually dispersing over hundreds of millions of years. Triton is doomed on a timescale that makes the word meaningful only in geological terms. The approach of this tidal doom has a warming effect on Triton's interior. As the orbit shrinks and circularizes, the amplitude of tidal flexing decreases, but the total tidal heating over the remaining orbital lifetime, integrated forward, is sufficient to have warmed Triton's interior substantially compared to what it would be without Neptune's influence. Models of Triton's interior suggest the presence of a subsurface liquid layer, a mixture of water and ammonia in proportions that depress the freezing point to as low as -90 degrees Celsius. If this ocean exists, it would be sandwiched between the rocky silicate core at depth and the overlying ice shell, maintaining its liquid state through a combination of tidal heating, residual radioactive decay, and the antifreeze properties of dissolved ammonia. The temperature of such an ocean would be far below any human comfort range, but it would not be below the limit for all known biology. Certain microorganisms on Earth, living in Antarctic ice brines and deep subglacial lakes, tolerate temperatures below -20 degrees Celsius. Whether life could exist in an ammonia water ocean at -90 degrees is unknown. The chemistry of such an environment, the available energy sources, and the viscosity of the solvent at that temperature all raise challenges. But it is not thermodynamically impossible in the way that solid ice at -235 degrees would be. A proposed NASA mission called Trident, studied as a candidate for the agency's Discovery program, would use a gravity-assist flyby of Jupiter to reach Neptune and conduct a Voyager 2-style flyby of Triton with modern instruments, a magnetometer to search for a subsurface ocean, a mass spectrometer to analyze the plume material, a camera capable of mapping the unseen hemisphere that Voyager 2 never photographed. The mission was not selected in its original competition, but the scientific case for returning to Triton remains compelling. The Moon has been visited once by a spacecraft carrying 1980s technology for a few hours, a third of a century ago. The hemisphere that Voyager 2 mapped was the summer hemisphere, the phase in sunlight during Neptune's current slow orbital season. The winter hemisphere, currently in darkness, has never been imaged. It may bear entirely different geological features, and the patterns of plume activity across it may be quite different from the southern polar geysers that were the most dramatic finding of the Voyager encounter. A person standing on Triton would see Neptune in the sky 10 times larger in angular diameter than our full moon appears from Earth. That image alone, a blue-green gas giant filling the sky above a frozen nitrogen landscape with the sun reduced to a bright point indistinguishable from a very bright star, captures something of the strangeness that the outer solar system represents. Of all the moons in the solar system, none is more violent, more geologically extreme, or more unlike any other known body than Io. It is Jupiter's innermost major moon orbiting at a distance of 422,000 kilometers, well inside the radiation belts that make Europa's surface lethal. Io's diameter is 3,643 kilometers, almost identical to our moon's. But there the resemblance ends. Io is the most volcanically active body in the solar system. It is not one of the most active. It is the most at any given moment. Dozens of volcanoes on its surface are erupting. Its surface is continuously reshaped by lava flows, ash deposits, and sulfur dioxide frost. The oldest features on its surface may be only a few thousand years old. Impact craters, which accumulate on the surfaces of geologically quiet bodies over billions of years, are essentially absent on Io. Any crater that formed would be buried under new volcanic material within a geologically negligible time. This violent character was not anticipated before the Voyager 1 flyby in March 1979. In the days before closest approach, a planetary scientist named Stanton Peele, working with colleagues Patrick Casson and Ray Reynolds, published a paper in the journal Science predicting that Io would be geologically active due to tidal heating. The paper appeared just 3 days before Voyager 1's closest approach. The images that came back showed a surface covered in colorful volcanic deposits, enormous calderas, and bright lava flows. And crucially, a navigation engineer named Linda Morabito noticed a crescent-shaped feature in one image that was too bright and too large to be another moon. It was a volcanic plume rising 300 kilometers above Io's surface. Peele's prediction had been confirmed almost literally hours after it was published. It remains one of the most dramatic instances of theoretical prediction confirmed by observation in planetary science history. The source of this extreme activity is the same mechanism that maintains Europa's subsurface ocean taken to a far greater extreme. Io is in orbital resonance with Europa and Ganymede, its orbit slightly elliptical, not perfectly circular. As it moves along this elliptical path, the distance between Io and Jupiter varies, and so does the intensity of Jupiter's tidal pull. This varying pull flexes Io's interior with a period of 42 hours. The friction generated by this flexing is dissipated as heat. The total heat generated by tidal flexing on Io is estimated at roughly 100 trillion watts. More than 30 times the total heat flow from Earth's interior, concentrated into a body the size of our moon. This heat drives an intensity of volcanic activity that has no analog elsewhere. Io's surface is painted in shades of yellow, orange, red, white, and black. The products of sulfur in its various allotropic forms and the silicate rock of lava flows at different temperatures. White regions are dominated by sulfur dioxide frost. Yellow sulfur marks flows of cooled sulfur. Red sulfur, less stable and more reactive, forms closer to active vents. Black basaltic rock marks the freshest lava, still too hot to have developed any sulfur coating. The result is a surface that in color-enhanced images looks less like a moon and more like an abstract painting. The volcanic structures on Io include features called paterae, caldera-like depressions that serve as the sites of lava lakes, lava floods, or eruption vents. There are more than 150 known paterae. The largest is Loki Patera, a roughly elliptical depression 202 kilometers across, containing a lava lake that periodically overturns the cooled, dark crust on the lake surface, gradually subsides under the weight of accumulated material, allowing fresh lava to resurface from below. This overturn process has been observed to occur roughly every 540 days. Loki Patera alone radiates more thermal energy than all of Earth's combined volcanic activity. Among the most spectacular features ever imaged on Io is Tvashta Catena, a system of paterae in the northern hemisphere that produced one of the most dramatic volcanic displays ever recorded. Images from the Galileo spacecraft in 2000 captured what appeared to be a curtain of lava founaining across a segment of Tvashta's floor, with a line of fire, a lava curtain roughly 25 kilometers long, glowing at temperatures measured at over 1,600 degrees Celsius. These temperatures are hotter than any lava erupted on Earth's modern surface, consistent with the style of volcanism believed to have dominated the early Earth, when its interior was much hotter than today. Io may offer a window into what Earth's geology looked like more than 3 billion years ago. When the New Horizons spacecraft flew past Jupiter in 2007 on its way to Pluto, it caught Tvashtar in full eruption, the plume towering 330 kilometers above the surface, captured in a sequence of images that showed the umbrella-shaped eruptive column in detail no previous mission had achieved. Io's mountains, unlike its volcanoes, are not volcanic in origin. They form instead by compression. The continuous addition of volcanic material to Io's surface raises the thickness of the crust, layer by layer, building up compressional stress that eventually buckles and lifts sections of older crustal material upward. The result is fault block mountains, tilted slabs, and ridges of ancient rock being pushed above the surrounding plains by the accumulating weight of new volcanic deposits. Some of these mountains reach extraordinary heights. Bozaule Montes rises approximately 18.2 kilometers, almost twice the height of Everest. Euboea Montes rises to a comparable altitude and extends across a larger horizontal area, making it one of the most imposing isolated topographic features in the solar system. Essentially, all of Io's mountains are at some stage of collapse, their flanks cut by large landslides, their bases buried in talus, accumulated from continuous erosion driven by the seismic activity of a moon that never stops shaking. The eruptive plumes that rise above Eo's volcanic centers are among the most dramatic structures in the solar system. The largest persistent plume system, centered on the volcano Pele, generates an umbrella-shaped column rising roughly 300 kilometers above the surface. The plume material traces a characteristic ring of dark red sulfur compounds on the surface, covering an area hundreds of kilometers across. Smaller plumes from different volcanic centers have their own characteristic footprints. In 1979, when Voyager 1 photographed Io for the first time at close range, mission scientists initially did not notice the plumes. They looked like photographic artifacts before Linda Morabito recognized them as something real. Within days of the Voyager 1 encounter, theoretical predictions that Io would be volcanically active were dramatically confirmed. One of the most active eruptive systems observed by the Galileo spacecraft was Prometheus, a vent that has been erupting continuously since at least Voyager 1's 1979 flyby. In the 18 years between Voyager and Galileo, Prometheus's lava flow extended 75 to 95 kilometers westward from its vent, advancing steadily across the frozen sulfur dioxide plains. The heat of the flow sublimates the sulfur dioxide frost ahead of it, and the gas recondenses as frost just beyond the flow's edge, producing the bright white ring that surrounds Prometheus in every image taken of it. In 1997, a single eruptive event from the vent system of Pilan Patera deposited more than 3,500 square kilometers of fresh, dark lava in a matter of weeks. When Galileo's camera recorded the aftermath, an entire region of the surface that had previously been covered in the bright reddish deposits of Paley's plume was buried under black basalt. The scale of this event had no direct analog in the terrestrial geological record. Ra Patera, a large shield-like volcanic structure in Eo's equatorial region, provides an example of longer-term volcanic evolution. Voyager images from 1979 showed Ra Patera surrounded by colorful lava flows extending several hundred kilometers from its center, in a radial pattern suggestive of multiple eruption episodes from the same central vent over time. By the time Galileo arrived in the 1990s, Ra Patera's appearance had changed. New flows had extended across areas previously captured by Voyager, and the color distribution around the vent had shifted, reflecting the cooling and chemical alteration of more recently emplaced material. Ra Patera is not dramatically active in any single image. It is not producing a major plume or a spectacular lava curtain, but it represents the baseline continuous volcanic activity that characterizes Eo's surface even in its quieter moments. Every square kilometer of Eo's surface is resurfaced by volcanic deposits at an average rate of perhaps 1 centimeter per year. Across the entire surface, averaged over geological time, new material is being added at a rate sufficient to bury the whole surface to a depth of several kilometers every few 100 million years. This resurfacing rate means that Io's geological memory is extraordinarily short. On Earth, rocks 4 billion years old survive at the surface in the cores of ancient continental shields. On Io, nothing from the time of its formation remains accessible at the surface. The entire visible surface is geologically modern, young enough in some regions that no geological timescale longer than human historical memory applies to it. In late 2023 and early 2024, NASA's Juno spacecraft, which had been extending its mission to study Jupiter's moons, conducted the closest flybys of Io since the Galileo spacecraft ended its mission in 2003. These flybys brought Juno within 5,100 kilometers of Io's surface, close enough for its infrared camera to produce thermal maps revealing dozens of active volcanic centers glowing in the night hemisphere. Several eruption sites that had been dormant or undetected in previous surveys appeared newly active. The degree of volcanic activity captured in those flybys reinforced the picture of Io as a world in essentially continuous geological transformation. Io has an atmosphere, seen by any terrestrial standard, composed primarily of sulfur dioxide. The source is volcanic outgassing, supplemented by sublimation of sulfur dioxide frost from the sunlit surface. When Io passes into Jupiter's shadow, the surface temperature drops rapidly, and the sulfur dioxide atmosphere freezes out, precipitating as frost over the night side before sublimating again as the sun returns. This periodic collapse and regeneration of the atmosphere is unlike anything observed on any other solar system body. The collapse happens quickly within minutes of Io entering eclipse, and the recovery as sunlight returns is comparably rapid. Ground-based observations have tracked this cycle in real time, watching the spectral signature of sulfur dioxide gas build up and fade as Io passes in and out of Jupiter's shadow. Io contributes material to Jupiter's magnetosphere at a rate of roughly 1 ton per second. Volcanic activity continuously releases gas and dust from the Moon's surface. Some of this material is stripped away by the intense particle bombardment of Jupiter's radiation environment and becomes ionized. The resulting plasma accumulates in a torus, a donut-shaped band of electrically charged material centered on Io's orbit, wrapping around Jupiter in a ring hundreds of thousands of kilometers wide. This structure, called the Io plasma torus, is a significant component of Jupiter's magnetic environment. The plasma in the torus interacts with Jupiter's magnetic field, generating electrical currents that flow along magnetic field lines between Jupiter and Io, connecting the two bodies in a circuit that carries roughly 10 million amperes. This interaction, known as the Io flux tube, produces electromagnetic radiation that can be detected from Earth, and that has been studied as a kind of natural monitor of volcanic activity on Io. When a major eruption occurs on Io, the increased outgassing enhances the plasma torus, which in turn affects the intensity and distribution of the electromagnetic emissions. Astronomers on Earth can detect changes in Io's volcanic activity by monitoring radio signals from Jupiter, an indirect but powerful form of remote sensing. The sulfur chemistry on Io's surface is extraordinarily complex, and understanding it has been one of the persistent challenges of Io science since Voyager. Sulfur exists in several distinct allotropic forms, molecular arrangements that differ in their physical properties and their colors. The bright yellow deposits that give large areas of Io their characteristic color are chains of sulfur molecules in their most stable room temperature form. At lower temperatures, sulfur can form polymers that are red or brown. At higher temperatures near active vents, sulfur vaporizes and redeposits as fine-grained white or yellow frost. Sulfur dioxide, the most abundant atmospheric gas, freezes as a bright white material that covers much of Io's equatorial region. The result of all these competing processes is a surface where the color at any given point reflects not just the chemistry, but the thermal history, how recently the material was heated, to what temperature, and how long it has been cooling. Reading the color map of Io is, in effect, reading a geological history written in the language of sulfur phase diagrams. The measurement of Io's total heat flow, the rate at which heat escapes from the interior to the surface, has been one of the critical constraints on models of the Moon's interior. Instruments on the Galileo spacecraft and ground-based thermal measurements have collectively established that Io's total heat output is roughly 100 trillion watts, or about 100 terawatts. This is the heat that must be continuously generated by tidal flexing to balance what the surface radiates into space. Dividing this by Io's surface area gives an average heat flow per unit area of roughly 2.5 watts per square meter, about 40 times the average heat flow from Earth's interior. But this average conceals enormous spatial variation. Near active volcanic centers, local heat flux measurements have exceeded thousands of watts per square meter. In the coldest regions between volcanic centers, the heat flow approaches the theoretical minimum consistent with the surface temperature. What did Io look like at the beginning of its history, before tidal heating established itself as the dominant geological process? The answer is almost certainly very different from today. When the solar system was young and Jupiter was still contracting and radiating enormous amounts of heat, Io's vicinity was too warm for water ice to be stable in the infalling material that was accreting to form the Moon. So Io formed without a significant water inventory from the outset, dry, rocky and iron-rich. As Jupiter cooled and the Laplace resonance locked Io, Europa and Ganymede into their current configuration, tidal heating ramped up to its current intensity. The process of differentiation, the separation of Io's interior into a metallic core and silicate mantle, may have been enhanced or even completed by tidal heating rather than by the primordial heat of accretion, making Io's geological history fundamentally different from that of any planet. Io also has a neutral cloud of sodium, potassium, oxygen and sulfur atoms that extends from its surface outward to roughly 6 times the Moon's own radius before dispersing into the broader Jovian system. These atoms originate in the upper atmosphere, where collisions with particles from the plasma torus knock them loose. They drift outward through the zone where Io's own gravity still exceeds the tidal pull of Jupiter, forming an extended halo around the Moon that is more tenuous than any atmosphere but detectable by spectroscopy from Earth. The sodium cloud was first detected in the 1970s from ground-based telescopes. The bright yellow emission of sodium atoms excited by solar ultraviolet radiation was recognizable by its wavelength even without the detailed spatial information that spacecraft would later provide. The interior of Io is as extreme as its surface. Models constrained by measurements of the Moon's gravity, topography, and the magnetic field observations of the Galileo and Juno spacecraft point to a structure in which a global layer of partially molten rock and a stenosphere or magma ocean exists at a depth of roughly 50 kilometers below the surface. This molten layer may be as much as 50 kilometers thick, making up perhaps 10% of the Moon's total mantle volume. Its temperature reaches about 1,500 degrees Celsius. Whether the molten material is distributed evenly through this zone, forming a true global magma ocean, or concentrated in discrete pockets connected by channels, remains uncertain. A global magma ocean would profoundly affect how Io's interior convects. The heat transport mechanism would be dominated by large-scale circulation of the magma rather than by solid-state convection in the silicate mantle above. The different heat transport modes produce different surface distributions of volcanic activity, and comparing those predictions to the observed pattern of hotspots and eruptions is one of the methods scientists use to constrain interior models. Io's composition is unlike that of any other moon in the outer solar system. While Europa, Ganymede, Callisto, Titan, Triton, and dozens of smaller icy moons are dominated by water ice, Io has essentially no water. Its high density, about 3.5 grams per cubic centimeter, similar to the Moon's density, is consistent with a composition of silicate rock and iron with no significant water ice component. The absence of water is thought to reflect the conditions at Io's formation location. Close to a young, luminous Jupiter, whose heat drove volatile water out of the material that would become Io before the Moon finished forming. The same heating that made Io too hot for water retention left the more distant Galilean moons cold enough to incorporate enormous quantities of water ice into their bulk composition. This gradient, rocky and dry at Io, progressively icier at Europa, Ganymede and Callisto, is preserved in the current bulk densities of the 4 moons, which decrease systematically with distance from Jupiter. Io is geologically alive in a way that makes every other solid body in the solar system seem inert by comparison. It is a world perpetually being remade. The surface that exists today will not exist in any recognizable form a million years from now. The heat of Jupiter's gravity pours continuously into its interior and is discharged through hundreds of volcanic centers in an unending cycle of eruption and burial. What Io teaches us ultimately is that the Moon can be more dynamic than a planet, that the energy input from tidal resonance can drive geological activity at rates and scales that no internal heat source alone could sustain. In that sense, Io is not just a remarkable object, but a proof of principle. Given the right gravitational geometry, the universe can keep a world hot almost indefinitely, regardless of its size. Io also forces a recalibration of how we think about habitability in the most extreme environments. Nothing is expected to live on Io. The surface temperature oscillates between the merely frigid and the incandescently lethal. The surface is sterile by any standard we can conceive. Yet the same tidal engine that sterilizes Io's surface is precisely the mechanism that maintains Europa's ocean in a state warm enough for liquid water and possibly life to persist. Io and Europa are products of the same force applied at different distances from the same planet, producing outcomes at opposite ends of the geological spectrum. The violence of Io and the quiet possibility of Europa are not opposites in any meaningful cosmic sense. They are two expressions of the same physics. This is perhaps the deepest lesson the Galilean moons have to offer. That energy, in the right form and at the right scale, is simultaneously the most destructive and the most life-permitting force in the outer solar system. We began this journey at Europa, beneath whose ice an ocean may harbor life. We passed through the gallery of strange objects that drift through and past our solar system, and through the layered interior of Ganymede, and across the fractured face of Mimas, and among the ancient rubble of the asteroid belt, and to the frozen polar deserts of Triton. We end at Io, where the violence of planetary science is most immediate and most visible. The solar system is not a collection of static objects. It is a system, dynamic, interconnected, still in motion after 4.5 billion years. The same gravitational resonances that created Io's volcanism also protect Europa's ocean and warm Ganymede's interior. The same processes of collision and disruption that scarred Mimas and Vesta and Ceres also launched Oumuamua outward from some distant stellar system. Every world we have visited in this account is in some relationship with every other, and that web of relationships is what defines a solar system rather than just a collection of isolated bodies orbiting a star. The connections are not abstract. The orbital resonance that drives Io's volcanic heat also maintains Europa's liquid ocean and contributes to Ganymede's magnetic dynamo. The same Jupiter whose gravity carved the Kirkwood gaps in the asteroid belt, and whose tidal forces will eventually shred Triton, also captured Io in a configuration that makes it the most geologically active body in the solar system. Saturn's rings, in their temporary brilliance, owe their structure to resonances with moons like Mimas. And the plumes of Europa, if they carry biological material from the ocean below, are themselves a product of the same tidal engine that elsewhere boils Io's surface rock. The pace of discovery is accelerating. When Voyager 1 and 2 made their grand tours of the outer solar system in the late 1970s and 1980s, the total number of confirmed moons of Jupiter was 16. Today it is approaching 100. Saturn's moon count has similarly grown from fewer than 20 known moons at the time of Voyager to more than 140 today. most of them small, irregular bodies captured from the outer solar system. Each new moon represents a new data point about the history of its host planet and the environment in which it formed. Each new mission, Europa Clipper, JUICE, Dragonfly, the proposed Enceladus, or Orbilanda, the planned return to the Neptunian system, will add layers of detail to a picture that was barely sketched when humans first sent spacecraft beyond the asteroid belt. There is also a broader context that it is easy to lose in the specifics. Every moon, asteroid, and interstellar visitor discussed in this account is a material object: rock, ice, metal, gas, made of atoms that were forged in stellar interiors and scattered by stellar explosions billions of years before the sun ignited. The water in Europa's ocean, the nitrogen in Triton's atmosphere, the iron in Io's core, the carbon in the Ryuk samples returned to Earth. All of it has a history measured in billions of years and spanning multiple stellar generations. The question of whether any of that material has organized itself, somewhere in this vast and ancient system, into structures capable of metabolism and reproduction is not just a scientific question. It is one of the oldest questions humanity has ever asked about its place in the universe. How much of it remains unknown is staggering. The ocean of Europa has never been sampled. The plumes of Triton have never been analyzed up close. The full complexity of Io's interior structure remains unresolved. Ganymede's multiple ocean layers exist in models. They have never been directly measured. The identity of Oumuamua's home system is unknown and may never be determined. The age of Saturn's rings and the mechanism of their formation is still being debated from Cassini data years after that mission ended. Even the simple count of significant moons in the outer solar system continues to grow as telescope technology improves. Jupiter now has nearly 100 known moons, most of them small, captured bodies discovered in the last 2 decades. In the decades since the New Horizons mission flew past Pluto and revealed it to be a geologically active world, with mountains of water ice, nitrogen ice plains, a haze-filled atmosphere, and a possible subsurface ocean. The category of what might be alive and interesting has expanded to include nearly every substantial icy body in the solar system. The discovery of Enceladus's active plumes, the mapping of Ceres's bright spots, the thermal imaging of Mimas's surface, the detection of water vapor above Europa. All of these findings have accumulated into a new picture of the outer solar system as a region full of liquid water, chemical energy, and geological activity, a picture that would have been considered speculative, even fantastical, a generation ago. That expansion is the most significant development in planetary science of the last half-century. Life, or the conditions for life, is not the exclusive property of a narrow habitable zone around a single type of star. Tidal heating, radioactive decay, and chemical energy gradients can maintain liquid water and possibly biology far beyond the reach of sunlight. The solar system that once seemed mostly empty and cold beyond the inner planets is now understood to contain more liquid water, more chemical energy, and more geological activity than anyone imagined when the first spacecraft flew past Jupiter in 1973. One of the greatest challenges facing the next generation of planetary scientists is not finding places where the conditions for life might exist. There are many, but developing the instruments sensitive enough and the missions capable enough to look for life itself in those places. Looking for life in the ocean of Europa is a different scientific problem from looking for mineral deposits on Vesta. It requires not just chemical analyzers but biosignature detectors. Not just cameras, but tools capable of distinguishing the products of metabolism from the products of abiotic chemistry. These tools are being developed. The techniques of astrobiology, the science of life in space, are growing more sophisticated with each mission, each laboratory experiment, each returned sample. The solar system is old enough, and complex enough, and strange enough, that it continues to produce surprises even after centuries of observation and decades of spacecraft exploration. Europa may contain life. Triton may have an ocean. Mimas may wobble because water sloshes inside it. An interstellar object may have already crossed our sky carrying material from a planet that no human will ever see. Saturn's rings, which have defined the visual image of the solar system in the popular imagination for hundreds of years, may be younger than the dinosaurs and already disappearing. There is a great deal more to discover. The instruments are being built, the missions are being planned, the questions are becoming more specific and more interesting with every answer that arrives. And somewhere out there, beneath the ice of a moon circling a planet circling a distant star, the same physics is probably operating, the same tidal forces, the same hydrothermal chemistry, the same quiet persistence of water in the dark, producing the same conditions that we are now, for the first time beginning to learn how to look for